Okay, let's start. So welcome to lecture number 4 for the course CSE3019 Software Quality and Reliability. Am I audible?
Yes, sir.
Yes, sir.
So yes, okay, thank you. So yesterday, that is in lecture 3, we learned the software quality architecture and the very first component of it called the pre-project component. Today we will learn about the defect removal policy and defect removal component. So we will first briefly recall the software development lifecycle models along with the classic waterfall model. You already know it, but still will recap. Otherwise, it will be very difficult to understand all the things we are going to discuss today. So we will briefly recap the software development lifecycle model. So along with this classic waterfall model, we'll also briefly recall other development models such as the prototyping models, the spiral model, and object-oriented model, and so on. So then we will know the factors affecting the intensity of this quality assurance activities in the development process. We will also recall the three terms called verification, validation, and qualification in the current context. And finally, we will learn a model for software quality defect removal, effectiveness, and cost. So let us go one by one. So this is the classic software development lifecycle model, which is generally termed as waterfall model because of its nice set. So in this model, you know that first requirements are collected, requirements are gathered from the user for whom you are going to develop the software. Then those requirements are analyzed. So after gathering the requirements, then those are analyzed and then requirements specified, analyzed, and based on those requirements, some design is prepared, software design is done. Then according to the design, coding is done, and after completing the coding, testing is done, and then the software or the product is installed or deployed, and finally a maintenance team is there to maintain the software. So in this model, you may have noticed that after completion of each phase, another phase can be initiated. Then after completion of that phase, then again another phase can be initiated. So that's why it is called a waterfall model, a step-by-step process. So this is the basic waterfall model. After that, an advanced waterfall model was proposed, where the loop is there. Means you can go back to the an initial state. In original classic waterfall model, no option was there like this. But in this advanced waterfall model or iterative waterfall model, you can go back to a previous stage, taking the feedback of the customers or finding some error, you can rectify those, and again you can proceed accordingly. So this is the basic difference between this basic waterfall model and this iterative waterfall model. Then we have also learned this prototyping model in an earlier course like software engineering. So in case of prototyping model, first and one thing here can be noted that these models are not alternative to each other. Sometimes you have to use the concept of waterfall model within this prototype model itself or within the spiral model itself. So these are complementary, not alternative. So here again, in case of the prototyping model, you have first this requirement are gathered, requirement are collected from the users. So this requirement gathering, design, documentation, then code and implementation, all these development life cycle are followed within this model also. But here the steps are somehow different. So first here this requirement definition by the customer. So sometimes the development team itself help to define the requirement. So they help the customer to do that. Then according to this requirement, some prototype is designed. Then prototype is implementation. So basic prototype is implemented. Then prototype is evaluated by the customer, not the development team. This prototype are generally evaluated by the customer. So there are many kinds of prototype like low fidelity prototype, medium fidelity prototype, high fidelity prototype. So I'm not going into these details, but here for the timing, you just remember this. The basic prototype is first created, then the customer evaluate that prototype. If requirement are fulfilled, then systems test and acceptance test is done. The system test is done. The development is acceptance test is done by the customer, and then system is deployed and maintained. If the customer is not happy with this prototype or their requirements are not fulfilled, then they demand further correction, changes, and some additional requirement can also be added. And then again, according to that, the prototype, the next level of prototype is designed, implemented, and again, sorry, again it is sent to the customer to evaluate. If customer again not satisfied, then this cycle continues and until they satisfied, and after satisfaction the system is tested for this system test and acceptance test, and then system is deployed as told earlier. The next is spiral model. Here there are mainly four phases called planning, then evaluation by the customer, sorry, planning, then risk analysis and resolution, then engineering, software engineering tasks are done here, then evaluation by the customer. So first, planning is done based on the customer comments. So whatever customers are demanding or whatever their requirements are, based on this some planning are done. Then in that plan, the risk is analyzed with how what type of risk are there to implement this one. So in this spiral model, this risk analysis is emphasized. Then after this risk analysis and risk evaluation done by the team, an initial prototype is made. Then the customer evaluate that. See here again the all the development life cycle process are followed. Maybe not exactly whatever there in the waterfall model, but some of them are followed. Like planning is there, requirement gathering is there, then designing is there, then building or coding is there, then customer evaluation is there. So all the some of this, not all, but some of the stages are also followed. At the same time, here you can see that prototype model is also there, which is implicit. So it is not always the case that when you are following a particular development model or methodology, you can always follow a particular model. Not any basic model is followed. They follow hybrid model. So so this is continued in this spiral way. Then again second prototype is built. Then again it is evaluated by the customer, and if some changes are required, then those according to that planning is done, and this again risk analysis is done. Again the prototype, the medium fidelity prototype is built, and again the same process is continued in this spiral way. So that's why it is called spiral model. And this is a picture of advanced uh, spiral model. But this engineering task is divided into two subtasks. One is called design, another is to construction. And this customers evaluation part is also divided into two parts. One is customer evaluation and another is customer comments and change, requirement or request for changes. So similarly, this here the entire thing is uh, built through prototyping in a spiral way. So there is a small task for you. Are you listening to me? Hello, is there anyone? So there is a small task for you. You just draw some more line like this. Okay. And maybe say for example you stop here. Now your task is to label this. You may have to, I'm giving some hints, you may have to modify these labels as well. So you try to label all these things. Okay, so this is for your home task. You will probably understand the model in a more clear way. So if you are able to do that, then and if you are unable to do that, then also you tell me. I'll discuss in the next lecture, in next class. This is the object-oriented model. Let me zoom in. So in this case, the reusable components are emphasized. Means whether a particular project can reuse some of the models or some of the modules or some of the components of existing software product or existing other existing software product. So the entire process is based on this reusable component. So this reusable even when a new product is introduced or new product is developed, then these reusable components are built so that can be used for some future.
Sir, your voice is not audible. Not audible, sir, your voice.
Hello.
Yes, sir.
Hello, am I audible now? Am I audible now?
Sir, you're
Sir,
audible.
your
Okay, just give me 1 minute. The headphone is probably not working. Let me remove it.
Okay, am I audible now?
Yes, sir.
Okay, so this is the object oriented model where the object oriented concept is there, and here the reusable components is emphasized. I mean, when you are when you are developing a software, you have to first search for reusable components are there in the existing softwares or not. If it is available, then you have to just a minute. So the reusable library is there. So in that library, you have to search first if any existing modules are there or not. If any existing module is there which you can reuse for your software, then you can reuse those in your software, and then you send it to the for customer evaluation. If they satisfied, then you can install or you can deploy the software and perform these maintenance activities. If the customers are not satisfied, they will give some feedback, and then again you may search in the reusable library. If available, then do the same process. If not available, then you have to design and implement on yourself. Means you have to then define the requirement. You have to do the design, coding, testing, all the phases. So in this way, the object-oriented models, through object-oriented model, you can build your software. So now let us see what are the factors affecting intensity of quality assurance activities in the development process. So project lifecycle quality assurance activities are process oriented. In other words, they are linked to completion of project phases, accomplishment of the project milestone, and so on. And the second thing is the quality assurance activities will be integrated into the development plan that implements on one or more software development models. So like the waterfall model, the prototyping model, spiral model, the object-oriented model, whatever we have discussed. The intensity of the quality assurance activities planned or indicated by the number of required activities is affected by two factors, which all the factors, actually many factors are there. So all the factors are categorized into two groups. One is project factors group and another is team factors group. This in project factors group, the magnitude of the project is observed. Then technical complexity and difficulty is also observed. Then extent of the reusable software component is also whether there are any existing software or components are there which can be reused or not. And then severity of the failure outcomes of the project fails is also a main concern here. Then coming to this next group of factors, the the professional qualification of the team members is very important here. Whether the team members are intelligent enough or qualified enough to do the task, then team adequateness with the project and the experience in the area. Whether they have the experience in that area or not, and availability of the staff members who can professionally support the team, and familiarity with the team members. In other words, if some new staff members are there who are not familiar with this task, and they are not professional enough, then you have to train the team first. Then you will have the sufficient manpower to supply the product or to develop the product. So that's why all these are belong to these team factors. Now let us read this example. So a software development team has planned the quality assurance activities for its new customer club project. The current project contract signed with a leading furniture store is the team's 11th customer class project dealing with the last 3 years. That means they have already built 10 such projects or small project in last 3 years. The team estimates that about 7 man months need to be invested by the 2 team members assigned to this project, whose duration is estimated at 4 months. So they have estimated that 7 man months is needed to complete the project, and total estimated duration is 4 months. When within 4 months they can complete the project. It is estimated that reusable components library can supply 90% can be reused from the existing software. And as here it is mentioned that it is the 11th project, so similar type of say 10 project has they have been already done, so they can utilize or reuse the components, most of this component, 90% of this component from this existing software. So has identified 3 quality assurance activities. Those can be applied to develop this software and make it a quality software. So this is the 3 quality assurance activities. One is design review of the requirement definition, inspection of the design, and the third one is the to system test of completion software package. And they have also estimated that the design review may take maximum half of a day, so 0.5 days mentioned here. They have also estimated that the duration for correcting the errors while reviewing the requirement definition may take maximum 1 day, and the inspection of design may take 1 day, and correction, if any correction is required, that may take maximum of 1 day, and so on. So here the main consideration affecting this plans are degree of team acquaintance with the subject. Here the team is entirely acquainted with the subject, because they have see here mentioned that it is the 11th project, so they are already acquainted with this subject. And high percentage of software reuse, again as it is 11th software, similar type of software, so they can use maximum of this module from the existing softwares they have already made. Size of the project, so the size of the project is medium here, and severity of the failure result if the project fails. There is a very low chance to fail the project, because they have experience, they have already built some 10 such softwares in the past. So the severity of failure is very low here. Now see this example. So the this example also taken from this book. The real-time software development unit of a hospital information system department has been assigned to develop an advanced patient monitoring system. The new monitoring unit is to combine a patient's room unit with the control unit. The patient's room unit is meant to introduce with the several types of medical equipment supplied by different manufacturers, which measures various indicators of the patient's condition. A sophisticated control unit will be placed at the nurse's station with data to be communicated to cellular unit carried by the doctors. The project leaders estimate that 14 months will be required to complete the project. A team of 5 will be sufficient with an investment of total 40 man months. The project leader also estimated that only 15% of the components can be obtained from the existing softwares. That is, only 15% can be the reusable components. And the SDLC methodology was chosen to integrate application of these two prototypes of the patient's room unit and two prototypes for the control unit for the purpose of improving communication with the users and enhancing feedback of the comments at the analysis and the design phase. Now here you can guess that the complexity of this project, the size of the project, and the other things like number of reusable components, all these things are means very large, and at the same time more manpower is required, and you have to first as the most of the components you have to build your own. So you have to first build the prototype and then you have to test all these things. So the quality assurance activities are 15 here instead of 3, where in case of this the last example we have seen that there were only 3 quality assurance activities. Now as this project complexity and the size is large and there are other concerns, so instead of 3, 15 quality activities are there, such as design review of requirement definition, then design review of analysis of patient's room unit, then design review of analysis of control unit, then design review of preliminary design, then inspection of design plans, and so on. So 15 quality assurance activities are listed here by the team leaders. So here the main consideration affecting this plan set, the high complexity and difficulty of the system. The complexity is high, low percent of software reuse, a very few percentage, maximum 15% modules can be reused, and size of the project is large here, and there is high severity of failure outcomes if the project fails, because it is a real-time software and project is large, so the severity of the failure outcome is high here. So in this way, based on the complexity, difficulty, size, and the number of components or percentage of components which can be reused, and whether there is severity of failure outcomes if the project fails, so all these things are considered to list these quality assurance activities. So it's depend project to project, it depend product to product, varies product to product. Now let us recall 3 more terms. One is verification, another is validation, and third one is qualification. So as per the IEEE standard, the verification is defined as the process of evaluating a system or component to determine whether the product of a given development phase satisfy of the conditions imposed at the start of the phase. So in this case, the examiner just follows the development process, assuming that all the earlier development phases have been completed correctly. So this is the assumption here. For the verification, the examiner assume that the earlier development phases has been completed correctly. They have to just verify the current module or current portion, assuming that the other thing are done properly. So this is the verification. The validation definition based on this IEEE standard, the validation is defined as the process of evaluating a system or component during or at the end of the development process to determine whether it satisfies specified requirements or not. So in other words, validation represents the customer's interest by examining the extent of compliance to his or her original requirements. So comprehensive validation reviews tend to improve customer satisfaction from the system. So if the validation is done properly, if the validation is done in a comprehensive way, then the customers will be satisfied. Then the definition of qualification based on this IEEE standard again. So they have defined the qualification as the process used to determine whether a system or component is suitable for operational use or not. So in other words, qualification focuses on operational aspects where maintenance is the main issue. So the planners are required to determine which of these aspects should examine, in which quality of assurance activities these should be examined, and in which phase of the software development model. So that's why we have just recalled briefly the different models and models for software development, and software development including software development life cycle model like classic waterfall model, then prototype model, then spiral model, and object oriented model. So now we will learn a model for software quality, defect removal, effectiveness, and cost. The model deals with two quantitative aspects of an software quality assurance plan, consisting of several defect detection activities, which was the main topic of today's lecture: defect detection activities. The plan's total effectiveness is in removing project defects, and the total cost of removal of this project defects. How to plan to effectively remove the defect. So first detect the defect, then removing the defect, and what is the cost to remove those defects. The application of the model is based on the three types of data. So to do those, we require three types of data. One is defect origin distribution, means from where the defects are generated, whether the defects are generated or originated from the design phase, or from the coding phase, or from the requirement gathering phase, or from the testing phase. And then we defect removal effectiveness data is also required. So if I follow some quality assurance activities, how effective are they? Means suppose I follow the contract review process. So it may not remove all the defect. There may be the case that some defect, and it always happens that some defects remain. Means you cannot remove all the defects. So the quality assurance activities which we are following, how effective they are. So defect origin distribution data. This is the first data sheet which helps us to remove the defect, detect the defect, remove the defect, and estimate the cost in removing those defects. So origin here refers to the phase in which defects are introduced. Origins are distributed throughout the development process from the project initiation to its completion. An extensive survey was conducted to identify the origin of the defects. Mean how many defects are on which type of defects are originated from which phases. The survey was conducted by major software development industries like IBM and others. The survey result reveals that similar patterns of defect distribution is there for almost all type of software project. So they have identified that this pattern of this defect and source are similar somehow. And later it has also been observed by the software professionals or experts that the distribution pattern does not change even with the passage of the time. So it has been observed that majority of these defects are originated during coding phase. So you can see here 40% of the defects are generally originated from this coding phase, 30% from coding and 30% 10% from integration, and the other defects are generated from the other phases, like requirement specification 15%, then design 35%, then documentation 10%, and so on. Then the second data we record is defect removal effectiveness. So it is assumed that any quality assurance activity filters or rectify a certain percentage of existing effects, but not all of them. So it can be noted here that the most cases the number of removed defect is lower than the number of defective uh, detected defects. Mean many of the you may detect many of the defect by applying a policy or activities of software quality assurance, but that may not remove all the defects of the identified or detected defects. Some of them will remain. For example, the requirement specification review can filter out maximum 50% of the defect. So it is mentioned here. So this particular activity, particular quality assurance activities can remove the 50% of the detected defects. So this is called the defect removal effectiveness. How effective are they? Again, another example, design inspection. It can remove 60% of this detected defects. So these data will also be required to understand the model. And then cost of defect removal. So what is the cost to remove the defects or filter out these defects? This is listed here. So here I'd like to mention again, once all these data are valid, they are achieved through these empirical studies, extensive survey by major software industries like IBM and others. So it has been observed empirically that the cost of removal or detected defects varies by development phases. So cost increases substantially as the development process progresses, and this is also very valid point, that cost increases substantially as development process progressed. Means, for example, removal of a design defect detected in the design phase itself may require an investment of 2 to 3 working days, whereas removal of the same defect, if they are identified during in the later phases, for example, if they are identified in the acceptance phases, acceptance test phases, then that may require 40 to 50 working days, so 10-15 times more than the earlier ones. Means if if they are detected in design phase itself, it may take maximum of 2-3 days, 2-3 working days, whereas if it is detected in the later phase, like in testing phase, acceptance testing phase, then it may take 40 to 50 working days. The relative defect costs are enlisted here in this table. So for requirement specification, if it is identified in requirement specification, it may relative cost of 1 unit. Then if it is identified in design, that the removal cost is 2.5 cost units, and so on. See here the operation by customer. If a defect is detected or identified in this phase, then it may take 110 units. That is, it may cause you to it may result to force you to double the project budget. Means if you initially thought that budget is 2 crore, so it may take another 2 crore or more than that to complete the project. So the early detection will help you to save the cost as well. So the model, now let us understand the model. So the model, to understand the model, we have to remember that this model works on based on these assumptions. The first assumption is the development process is linear and sequential like waterfall model. A number of new defects are introduced in each phase, development phase. Say for example, some defect will generated in requirement specification phase. Then again, some new defect will be generated in design phase. Then again, some new defect will be generated in the design, coding, and subsequent phases. The third assumption is review and test software quality assurance activities serves as filters, removing a percentage of the entering defects and letting the rest pass to the next development phase. As I mentioned that if suppose n number of defects is detected, then say n minus m number will be uh, filtered out or removed, and the rest will be passed to the next development phase. And as I mentioned earlier, that if the number of incoming defect is 30 and the filtering efficiency is 60%, then 60% of this 30 means 18 defect will be removed, and 12 will be 12 will pass to the next stage. The fourth assumption is at each phase, the incoming defects are the sum of the defects. Incoming defects are the sum of the defects not removed by the former quality assurance activity and together with the new defects introduced in the current development phase. Mean if the previous defect is 12 and new defect is another 12, then the total defect is counted in phase 12 plus 12 is equal to 24. The cost of defect removal is calculated for each quality assurance activities by multiplying the number of defects removed by the relative cost of removing a defect. So cost has been shown in this slide, earlier slide. So if a defect removal policy or a quality assurance can remove 10 defects, for example, and the relative cost is 2, so the total cost will be 2 into 10, that is equal to 20 cost units. And the last assumption is the remaining defects unfortunately passed to the customer will be detected by him or her. In these circumstances, full removal entails the heaviest of the defect removal cost. As you can notice here, if the defect is identified by the customer, it will cost a lot. Now, each of these quality assurance activities, like some quality assurance activities I have shown earlier for the project example. So these are the quality assurance activities. So each of these, as I mentioned earlier, that this varies project to project. So each of these quality assurance activities is represented by a filter unit, as shown here for the design phase, for example. So for example, in design phase 35 defect has been detected, 35, and the past defects from the earlier stage is 7.5. So what is the number of defects? 35 plus 7.5, that is 40 42.5, correct? So, and the filter effectiveness is 50%. So among this, for 35 plus 7.5, that is 42.5, only 50% will be filtered out, or or hello, is there anyone?
Yes, sir.
So 50% will be filtered out, and rest of the 50% will be passed to the next phase, right? So this
Yes,
so 21.2 will be removed and 21.3, then only one digit has been taken, so that's why it is approximated in this way. So 21.3% 21.3 number will be removed, and the cost of this defect removal is relative cost is 2.5 cost unit. So total cost for this particular design phase will be 2.5 into 21.3, that is 53.2 units. Is it clear, this filter unit? So it is, so for every phase of this software development, there is a filter. Now the model represent the following quantities, that is phase originated defect, which is acronymed as POD, then PD, pass defect, and then percentage of filtering effectiveness, which has been shown earlier, the second table, and the RD is remove defect, how many defects are removed, and CDR is the cost of defect removal, and which relative cost I have shown earlier in a table, and then the TS is the total removal cost, which is equal to RD, that is the removed defects, number of removed defect, and the CDR means multiplied by CDR means the cost of defect removal. Now let us apply the model to a standard quality assurance plans. This is called a standard quality assurance plans, where there are 7 quality assurance activities, starting from requirement specification review to design review to unit test to operation phase. So there are 7 quality assurance activities, and defect removal effectiveness is 50%. Sorry, 50% for this requirement specification review, then 50% for design review, then 50% for unit test code, then 50% for integration test, and so on. That means, for example, 50% of the defect can be filtered out or removed if we follow this requirement specification review, and the relative cost is 1. Similarly, the 50% of the detected defect can be removed in the design review process, and the cost of each defect removed is 2.5 cost unit. So 15 will be say for example 15 is generated in this first phase, requirement specification phase. Then they are, as it is very fast stage, so there is no carry forwarded defect, so 15 plus 0, it is 15, and the percentage of filter effectiveness is 50%. So among this 15, only 7.5 will be removed, and 7.5 number of defect will be passed to the next phase. So this and cost of this defect removal, the relative cost is 1 unit one cost unit. So the total cost is this particular phase. Then in the design phase, we have seen that 7.5 has been carry forwarded. So, and in this phase 35 defect is generated. So the total number of defect will be 35 plus 7.5, and the cost effective sorry, filter effectiveness is 50%. So 35.7.5, this is 42.5. So 50% of 42.5 is 21.2. So 21.2 will be passed to the next phase, and rest of this will be defect will be removed or filtered out, and cost for removal each defect is 2.5. So total cost is 53.2 sin. So in this way, if we go through all these phases, then the final total cost is in this phase is 759 cu. So in this way we can proceed, or you can we can follow this model to calculate the total removal cost of the all the defects identified, all the defects identified. So now let us apply the same model to a comprehensive standard quality assurance model. First one was the standard defect filtering system. Now it is a comprehensive standard quality assurance plan. Here, other than this, those 7 quality assurance activities, 2 additional quality assurance activities are included, like design inspection and code inspection. And as you are inserting more quality assurance activities, the and each quality assurance activities will remove some of the defects, so more number of defects will be removed. And and it is probably very clear that if the number of detected defects is more, then it will cost more. Means each of these defect removal has some cost, relative cost. So more, in this case, more number of defect will be detected and the cost will be increased, but you will finally get a better quality of software, as number of defect will be will be defect removed here will be high. So if we apply the same model in the similar way, we can see that there are, instead of 7, 9 filters are there. So in this way we can calculate the total removal cost for every phase. And if we compare the two standard quality assessment plan, like standard and comprehensive quality assessment plan, then we can see that the number of percentage of removed defect is high in case of this comprehensive quality assurance plans, and it is low in case of standard quality plans. And as the number of defect removed here is large, so that will obviously lead to the higher cost. Yes, sorry. Okay. Oh, so this is the last slide. So to summarize, we have learned, we have actually recalled the classic and other software development methodologies, and we also recall the factor, effective, intensity, quality assurance activities in the development process. We have also recalled the 3 important terms: verification, validation, and qualification. And we have finally learned a model for software quality, defect removal, effectiveness, and the cost associated with that. So whatever I have covered today, you can find it in Daniel Gallin book, Software Quality Assurance from Theory to Implementation, published by Pearson Education in 2004, sorry. And the most of the topic can be found in chapter 7, section I have forgot to mention, section 1.2 to section 7.2, 7.1 to 7.6. And you can read the entire chapter for better understanding if you are interested. So next class we will know about the reviews in detail. So if you don't have any specific question, then we can finish the lecture, today's lecture. Do you have any doubt?
No, sir.
Okay, thank you.